welcome student. Sem 6 CH6502 Unit 2 Quantum Chemistry. I am Dr. Devangar Pandya from Department of Chemistry, St. Xavier's College, Autonomous, Ahmedabad. Well friends, in our previous lecture we have discussed regarding the basic information of quantum chemistry, the application area of quantum chemistry, and some important theorem related to Hermitian operator. 5 theorems are there, so that we have discussed in our previous lecture. In today's lecture, we will going to discuss regarding setting up of operators for different observables. And after discussing that, we're going to discuss about different variables in Schrodinger equation. So application of Schrodinger equation to isolate different variables from the equation and the solution of that variables. So that much we are going to discuss in today's lecture. Well, as you know that to set up a quantum mechanical operator for different observables, when I said observables, it means it going to include different properties associated with the electron confined into an atom, like position of particle in space, position of particle from the nucleus and its distance between nucleus and the particle, kinetic energy associated with particle, potential energy associated with particles, total energy associated with particles. These are called different observables, and we need to set up quantum mechanical operator for that. So every physical property, as I have narrated earlier, like position, momentum, kinetic energy, etc., a system has corresponding quantum mechanical operator. So every physical property have a specific quantum mechanical operator. The physical measurable quantities of a particle already have mentioned, that is a position, which is represented either x, y or z depending on the coordinates. Momentum, that is represented as p. Kinetic energy, that is symbolized as t. Potential energy nu, and total energy E. Angular momentum, these are called physical measurable, these are called physical quantities, these are called different observables, these are called properties, etc. The operators correspond to these quantities we can found in this table. It will take a little time as it is animated. So every physical observables have different quantities and each quantities will be assigned with a specific quantum mechanical operator. As you can see here, the physical quantities are given in the tabular form. 8 physical quantities are there, and each these physical quantities have these quantum mechanical operators. Like if we want to indicate the position of electron in space in the atom, it can be represented by, suppose on x component, x direction in Cartesian coordinates, then x multiplied by x. So x dot x, that is the quantum mechanical operator for position. Position of particle from nucleus, then it is represented as r, and that is multiplied by small r. So r dot small r, that is the quantum mechanical operator for position. Similarly, if you want to represent quantum mechanical operator for momentum, then h upon 2 pi I d by dx, because it is x component. So that is the momentum operator, quantum mechanical operator on x component. Total momentum operator can be represented as h upon 2 pi I delta. Well, delta is a Laplacian operator and its meaning is d by dx, d by dy and d by dz. So it represents all x, y and z coordinates. Now quantum mechanical operator for kinetic energy is represented as minus h square upon 8 pi square m delta square, where delta square is d square by dx square plus d square by dy square plus d square by dz square. That is also a Laplacian operator in square. So that represent kinetic energy in three-dimension way. This is the quantum mechanical operator for kinetic energy. Now kinetic energy on x component, so instead of this three dimension we need to put x component, d square by dx square only. Then it is a kinetic energy on x component. Potential energy can be represented as V, and addition of kinetic energy and potential energy represent the total energy, or in other sense it is also known as Hamiltonian operator. So each physical variable, physical quantities, physical observable have a specific quantum mechanical operator. Now rules to set up this quantum mechanical operator. We need to set up rules for this quantum mechanical operator. Each physical variable have a specific quantum mechanical operator. So to represent that, we can show here the different rules associated with this quantum mechanical operator. If we want to indicate the position, yes, write down the expression for physical quantity in classical terms, in terms of Cartesian coordinates of position x, y, z and momentum px, py, pz. So you need to write down the expression of a physical quantity in a classical terms. Terms of Cartesian coordinates, that is position, can be represented as x, position can be represented as y and z. But if you want to represent momentum on x-axis, then it can be represented as px, momentum on y-axis py, momentum on z-axis pz. So that way you can represent. Replace the coordinates and momentum by their corresponding operator. That value can be replaced by their corresponding operator. As we have seen in the previous table, for px it is h upon 2 pi I d by dx. Similarly for py, h upon 2 pi I d by dy. Similarly for pz, h upon 2 pi I d by dz. So replace this coordinates and momentum by their corresponding operator. That means you need to replace px by h upon 2 pi I d by dx. Likewise, operators for a coordinates of say x is a multiplication by the variable itself. Operator for coordinates of momentum, say for example that is px, already I have said that px, then it can be represented as h upon 2 pi I d by dx. If it is py, then it should be represented as h upon 2 pi I d by dy. And if it is pz, then it can be represented as h upon 2 pi I d by dz. Likewise. Now to obtain a quantum mechanical operator for kinetic energy, if you want to get the kinetic energy that is represented as Tx, because it is on x direction of Cartesian coordinates of a single particle moving in one direction, that is x direction. So for that kinetic energy we want to obtain. Kinetic energy's value, you know that Tx is equal to 1 by 2 mv square, and because the movement we need to find out on x component, so it is written as 1 by 2 mx square, that is mv square only, not x square, mv square vx square, vx square. So 1 by 2, if we multiply this equation with m, divide it by m, we're going to get this one, 1 by 2 m square v square x by m, because we have multiplied it by m and divided by m. This is not x square, vx square, that you need to understand. Total vx square, velocities square. So tx can be represented as px square, because you know that 1/2 m square vx square, that is px square, upon 2m mv square, that is px, that is momentum, and m into v, that is momentum, m square into v square, that is momentum square, that is p square x, that is represented by p square x by 2m, where px would be is equal to m vx, m into vx, and p square x is equal to m square into v square x. Therefore, for kinetic operator, Tx is equal to minus h square upon 8 pi square m d square by dx square. Similarly, for Ty, it can be represented as h square minus 8 pi square m d square by dy square. And for Tz, that means kinetic energy on z component, it is represented by minus h square upon 8 pi square m d square by dz square. Now, how to obtain momentum operator? For an electron wave function, psi a is equal to a sine 2 pi I by lambda may be represented by a function psi is equal to a exponential plus or minus 2 pi I x by lambda, that is a time dependent wave function. Differentiating with respect to x, because x component is there, we have expected the movement on x direction. So differentiating with respect to x, we're going to get d psi by dx. If we put the value of psi over here, we're going to get the differentiation of a exponential plus or minus 2 pi I x by lambda as plus or minus 2 pi I by lambda a exponential plus or minus 2 pi I x by lambda. This value looks itself like wave function. So if we substitute the value of wave function psi over here, d psi by dx, we're going to obtain plus or minus 2 pi I by lambda into psi, because this value indicates itself as psi. So we substitute the value of psi over here, we're going to abbreviate the equation like this one, that is equation 2. But de Broglie's relation, where lambda is equal to h by p, so replacing the lambda in this equation, we're going to get d psi by dx plus or minus 2 pi h into px psi, or either it can be written as px psi is equal to h plus or minus h upon 2 pi I d by dx. So here when we replace psi from both the side, we're going to get the momentum operator. So psi is a function which, on being removed from the equation, reduce it to a differential operator, that is px hat, that is the symbol of operator, and that is written as plus or minus h upon 2 pi I d by dx. The operator px in the x direction is h upon 2 pi I d by dx, and in the negative x direction, px star, it is represented as minus h upon 2 pi I d by dx. So plus or minus, one is plus, that is in plus x direction, and one is minus, that is in minus direction. Similarly, py can be represented as h upon 2 pi I d by dy, that is on plus y side, and py star, that is minus h upon 2 pi I d by dy on minus y side. And similarly in Cartesian coordinates, pz, that is h upon 2 pi I d by dz, that is on plus side, and pz star, that is minus h upon 2 pi I d by dz on minus side of the z component. So this way you can get the momentum operator. Now we need to prove that this Px is Hermitian operator, and you know Hermitian operator is known as turnover rule, where that means it apply on operator one after the other and the value is going to be similar, then it is considered as Hermitian operator. And we need to prove that this momentum operator on x component is a Hermitian operator. So we need to apply on function one after the other, and if we will get the same solution for that application of operator on different individual wave function one after the other, then we can prove that this Px is a Hermitian operator. Say for example, we have wave function psi1 and psi2. Here we have taken the complex conjugate of psi1, that is psi1 star, and psi2, and we have this momentum operator which is written as h upon 2 pi I d by dx, and that is going to apply on psi2, we'll get one value. Then after we're going to apply it on psi1 star, we'll get another value. If this two value is similar, we can prove that this Px is a Hermitian operator, and that is taken in a blue color, you can see over here. So now when you take the integration of this, you can understand that h upon 2 pi I, that can be kept outside the integration. Psi1 psi2 star, psi1 star psi2, that is from minus infinite to plus infinite. So it can gives us a value h upon 2 pi I integration psi2 d by dx psi1 star dx, and that value of psi1 and psi2 are infinite, so the first term of right hand side turns 0. Therefore integration minus infinite to plus infinite psi1 star h upon 2 pi I d by dx psi2 can be represented as minus h upon 2 pi I integration psi2. Now this time here you can see that is on psi1 star dx. So integration minus infinite to plus infinite psi2. Now this time not psi1 star, this time psi2 is here, and the operator is going to operate on psi1's complex conjugate psi1 star dx, and can be represented in this way. It proves that the turnover rule for momentum is similar. That means this way you write or this way you represent, both is similar, and that is why we can prove that the turnover rule is there and momentum operator is a Hermitian operator, and it's a linear operator in a physical observables. Kinetic energy Tx of a single particle moving in one dimension box. We need to prove the new quantum mechanical operator, that is Hamiltonian operator. Hamiltonian operator is also known as total energy of the electron. So quantum mechanical operator for total energy or Hamiltonian operator, both are similar, and we need to find out that to establish a quantum mechanical operator for total energy of electron, or if somebody will ask you derive Hamiltonian operator for electron, both theory is going to be similar. The kinetic energy of a single particle moving in one direction x, that you need to understand. So the value of kinetic energy, as you know, 1 by 2 m v square x is equal to 1 by 2 m square v square x upon m multiplying m by m. So Tx is equal to p square x upon 2m, where Px is equal to m into vx. So p square x is equal to m square into v square x. Therefore, the kinetic operator Tx is equal to 1 upon 2m h upon 2 pi I. We have substituted now the value of Px over here. So substituting the value of Px, we are going to get h upon 2 pi I d by dx whole square. So 1 upon 2m, now h square, that is written as h square, 2 square, that is written as 4, pi square I square, d square by dx square, so it is written as d square by dx square, and hence this is written as minus h square. Why minus? Because I is equal to minus 1, under root minus 1. A root is missing over here, under root minus 1, and its square, when you are going to take, it is minus 1. So that minus symbol is over here. Minus h square upon 2 into 4, that is 8. 8 pi square m. Now I value we have taken as under root minus 1, and its square is equal to minus 1. So that minus is taken over here, d square by dx square. Similarly, potential energy operator, that is represented as V hat x, and that is the value of that is Vx. So the total energy H is equal to kinetic energy plus potential energy. So H is equal to kinetic energy operator, that is H minus h square upon 8 pi square m into d by dx square, that we have taken, and potential energy Vx we have taken. So Hamiltonian operator or total energy operator is written as the sum of these two. So that can be represented as minus h square upon 8 pi square. Now these are the variables, delta square I upon mi plus v. Here mi is the mass of a molecule I, and this is the Hamiltonian operator or the quantum mechanical operator for total energy of a particle. Now next one, we need to set up a quantum mechanical operator for angular momentum. And for angular momentum, we can obtain the value like classically angular momentum is given by the vector product of position r and linear momentum p. So when we take the vector product of position r and momentum p, we are going to get the quantum mechanical operator for angular momentum. So L is equal to r into p. If I, j and k are unit vector along x, y and z coordinate respectively, we are going to get r as ix plus jy plus kz and p as ipx plus jpy plus kpz. So this I, j and k, they are the vector unit, and x, y and z, that are the position of particle from the nucleus, and px, py, pz, they are the momentum. So L can be written as angular momentum operator. L can be written as ix plus jy plus kz into ipx plus jpy plus kpz. So L can be written as, suppose if we are going to keep I constant, we are going to get ypz minus zpy, and if we keep j constant, zpx minus xpz, and if we kept k constant, xpy minus ypx. So we have kept this I, j, k constant, and we're going to get this value. By definition of angular momentum, L is equal to I. This can be represented as Lx. This can be represented as Ly, and this can be abbreviated as Lz. So if we substitute that value, we're going to get this equation 2, where Lx, Ly and Lz represent the three components of angular momentum L. that means this Lx which has the value as ypz minus zpy represent the angular momentum on x-axis. Similarly, Ly, which have value zpx minus xpz, that is the angular momentum value for on y-axis, and this Lz, that is represented as xpy minus ypx, that is the angular momentum value on z-axis. So that Lx, Ly and Lz represent the three component of L. Replacing Px, Py, Pz by their corresponding operator over here, the operators for the three components of angular momentum can be obtained as this is the operator of angular momentum on x component, and we have value for x component, that is ypz minus zpy, ypz minus zpy. Now pz and py, that is the momentum kinetic operator, momentum operator, and if we substitute that value and kept h upon 2 pi I constant, it can be represented as y d by dz minus z d by dy. So that is the value of angular momentum on x. Angular momentum on y-axis can be represented as h upon 2 pi I z d by dx minus x d by dz. And similarly, angular momentum operator on z-axis can be represented as h upon 2 pi I x d by dy minus y d by dx. So that is equation number 3, and this addition, sum of these three, Lx plus Ly plus Lz, will represent the total angular momentum operator L for the system. Now application of Schrodinger equation for hydrogen atom, and we have to separate or isolate r, theta and phi variables from that equation. Electron exists in 1s orbital of hydrogen atom, rotate three-dimensionally surrounding nucleus. So the position and wave function can be indicated through the radial coordinates r, theta and phi. Instead of Cartesian coordinates, we need to convert it into radial coordinates, because in 1s orbital of hydrogen atom, when we think regarding three-dimensional rotation, then electron is rotating surrounding nucleus in the circular way. And when it rotates in a circular way, then instead of Cartesian coordinates, it is better to represent radial coordinates r, theta and phi for a moving electron in a circular way. According to Schrodinger equation, d square by dx square plus d square by dy square plus d square by dz square psi, that is Laplacian operator del square psi plus 8 pi square mu upon h square e minus v psi is equal to 0, where mu is equal to m1 m2 upon m1 plus m2. m1 and m2 are the mass of electron and nucleus of an atom. The electron execute rotational motion around or surround the nucleus in three dimensions. So its position and the wave function must be expressed in a spherical coordinates, like for radius it can be represented as r bracket r, for angle that is theta into theta, and for another angle phi into phi. So here in the figure you can see that this is the nucleus, and at arbitrary point P, suppose our electron would be there, then the distance between this source to P, that is represented as radius, and this will going to form two different angles, one with x-axis and the other with z-axis. The angle which it forms the imaginary point of the position in this plane, xy plane, that angle would be theta, and the real angle, that is position P with z-axis, can be represented by phi. So this r, theta and phi, they are radial coordinates, will indicate the actual exact position of this particle in space from different distance from nucleus. Now this is a point P and it has a d theta value, that is this value. D phi value should be here. So in three-dimensionally, if you want to show the position in space, the displacement can be represented as d tau. This is d phi, d theta and r is there. So that represents the position of this particle in space in x, y and z coordinates, and it is abbreviated as d tau. But we need to represent this position using r, theta and phi radial coordinates. So Cartesian and radial coordinates interconversion is required, and for that again this equation we have taken, this is theta, this is phi, or either you can write this one is phi, this one is theta, that is fine. This is our radius r and the point would be over here representing in all the three Cartesian system x, y and z. So if we want to replace x with radial coordinates, then it should be written as x2 minus x1, and for that the conversion of x into r, theta and phi can be written as r sin theta into cos phi. If you want to replace y, then its radial coordinates value can be written as y2 minus y1, and that is represented as r sin theta sin phi, and for z Cartesian coordinates the value would be r cos theta. This r is smaller one that you need to understand, z2 minus z1 r cos theta. So wherever x is there, you can replace it by r sin theta cos phi. Wherever y is there in Schrodinger equation, can be replaced by r sin theta sin phi. Wherever z is there in Schrodinger equation, can be replaced by r cos theta. So the position and wave function can be indicated through radial coordinates r, theta and phi. According to Schrodinger equation, d square by dx square plus d square by dy square plus d square by dz square, this is z square typological mistake, psi is equal plus 8 pi square mu upon s square e minus v psi is equal to 0. That is the Schrodinger equation. And here we have Cartesian coordinates. That Cartesian coordinates we need to change with these radial coordinates, where here the value of mu, that is m1 m2 upon m1 plus m2, where m1 and m2 are the masses of electron and nucleus respectively. So now that Schrodinger equation can be represented as little buffering is there, and we need to represent r, theta and phi base equation. So in this equation one, total energy has two parts: energy due to motion of particle and energy of electron in respect to proton. So two type of energy remain associated for the particle confined into hydrogen atom in 1s orbital. Two type of energy would be there: energy due to motion of particle and energy of electron in respect to proton. To obtain proper equation separating these two part of energy from the total wave function, linear motion is separated out. For this, new variables are added such as x, y and z, which are space coordinates, which are Cartesian coordinates, and exist in a middle part of the mass of hydrogen atom. And variable r, theta and phi are polar coordinates of electron in respect to nucleus. So Cartesian coordinates for hydrogen can be written as x is equal to mx m1 x1 plus m2 x2 upon m1 plus m2. Y Cartesian coordinates represented as m1y1 plus m2y2 upon m1 plus m2, and z can be represented as m1z1 plus m2z2 upon m1 plus m2. Now this x, y and z can be replaced by these radial coordinates, as x can be taken as r sine theta cos phi, already I have mentioned earlier. Y can be represented as r sine theta sine phi, and z can be represented as r cos theta. So when you substitute this value of x, y and z into Schrodinger equation, you can get another Schrodinger equation based on polar coordinates instead of Cartesian coordinates. Substituting this value into equation 1, we are going to get this value, and in that value you can found r, theta and phi base Schrodinger equation. So here you can see the value when you substitute into Schrodinger equation, you can get this kind of equation. This is also a Schrodinger equation. We have done nothing into this, just we have put the value of x, y and z Cartesian coordinates into this, and simplifying we're going to get this equation, which is based on r, theta and phi base equation. But there is a mixing of r, theta and phi. We need to isolate this variable from each other. So in respect with each different variable, we get different Schrodinger equation for hydrogen atom. So that we are going to obtain over here. This equation is a second order partially differentiation equation like Schrodinger equation. So it is nothing different, but it is a Schrodinger equation which you written in semester 1. But here instead of Cartesian coordinates, it has radial coordinates. So wave function can be written as r t theta phi phi f phi. And when you substitute the value over here, psi value, that can be represented as r t theta f phi, that is the wave function in a radial form, can be represented as 1 upon r square d by dr r square. Now instead of this psi, we need to put this value. So instead of psi, we can written r t theta f phi dr plus 1 upon r square sine square theta, that is 1 upon r square sine square theta d square psi. Instead of psi, we need to write r t theta f phi. So we substitute the value of psi over here as well, and we're going to get this second part. This is going to be your first part of equation, that way I am going to speak. This is going to be your second part of equation, and this is going to be your third part of equation. This will remain common to all the three part. So when you substitute value of psi over here, you get this second part. Here when you substitute the value of psi over here, you get the third part, where 1 upon r square sine square theta into d by d phi sine theta, and instead of psi you can put r t theta f phi d theta. Then 8 pi square mu upon h square e minus v. Now instead of psi, I can write r t theta f phi. Now according to the rule of differentiation, t theta f phi upon r square d by dr, because when the differentiation is based on r, only r component you can take there, and this t and phi can be kept outside. So that we have taken outside over here, upon r square, that is r square over here, d by dr r square. Now dr by dr by dr, and t theta and f phi kept outside. Similarly here, that is phi related double differentiation, so r and t theta should be kept outside. So r t theta upon r square sine square theta into d square f phi upon d phi square, plus here also d phi and here this equation is based on the theta differentiation, so t theta remain over here. R and Fy can be kept outside, so r Fy upon r square sine square theta d by d phi sine theta into, here you can take only theta base variable, so this is theta base variable, plus this remains the same, 8 pi square mu upon s square e minus v r t theta and Fy. Now dividing each term by t theta and Fy, that means you need to divide this equation both the side by this wave function t theta and Fy. You will obtain, see here, when this first part you will divide it by t theta Fy. T theta Fy is similar, so it will cut out and we are going to get 1 upon r square into 1 upon r square into t theta and Fy will going to cancel out each other, that you can understand. And I have changed the color because this is r variable base equation, which is represented into blue color. Now here when you divide it by t theta Fy, so r and t theta cancel out and it can be written as 1 upon Fy into r square sine square theta d square Fy by d phi square. This is phi base equation, also theta is there, but this majority is phi base equation, and phi base equation represented into this red or pink color. And this one is here when you're going to divide it by t theta Fy, r and Fy will cancel out each other, so 1 upon r square sine square theta t theta. T theta should be mentioned over here, that is mistakenly not written, but t theta would be there, d by d psi sine theta d t theta by d theta plus 8 pi square mu upon s square e minus v. Here also when you divide it by t theta Fy will cancel out each other, so we're going to get only this value. So this is also a Schrodinger equation, just we have done put the value of this variable based wave function, and then we're going to get this different variable based equation. Now in this equation we need to get the value of r base equation, phi base equation, theta base equation. So now each term is multiplied by r square sine square theta in the previous equation. We're going to obtain sine square theta upon d by dr r square dr by dr. So when you see the previous equation, you come to know that in this equation you need to divide it by r square sine square theta, multiplying this equation so that we can remove this part, r square sine square theta, r square sine square theta. So when you multiply this equation by r square sine square theta, you can remove this two part, and that is why we multiply this equation both the side by r square sine square theta. So multiplied by r square sine square theta. Here we will remove r square from this side, so sine square theta upon d by dr, r square dr by dr, plus here r square sine square theta will cancel out each other, so 1 upon Fy d square Fy by d phi square. Now you can see that this is the only phi base portion, for variable phi base portion. Now r square sine square theta, there r square sine theta, so sine square theta means sine theta will remain, and r square and 1 sine theta cancel out each other, so sine theta upon t theta d by d phi sine theta d t theta by d theta plus 8 pi square mu r square sine square theta. Here also we have multiplied upon s square e minus v is equal to 0, or can be represented as sine square theta d by dr r square d by dr plus sine. This portion we kept this side, so the plus will convert to minus, and this phi square equation, phi base equation, kept this side, So that is the only change between these two equations. That is equation number 5, where you can see the 5 base equation we have kept this side. Now equation 5, left hand side has only two variables, r and theta, where right hand side have phi. Here you can see this is a left hand side portion, and this left hand side portion contain r and theta variable, while this right side portion contain only phi base equation. So taking this minus 1 upon fy d square fy by d phi square as m square to abbreviate it, if this portion is symbolized by m square, sin square theta r, that is r variable, and it is represented into blue color, d by dr r square d by dr plus sin theta base equation can be represented into green color, sin theta upon t theta d by d phi is there as well, sin theta d t theta by d phi d theta plus 8 pi square mu r square sin square theta s square a minus v is equal to m square. So instead of phi base equation, we have abbreviated and put the value m square. This is equation number 6. Now this value 1 upon minus 1 upon fy d square fy by d phi square is equal to m square. So it can be this, if this will kept this side, it can be represented as d square fy by d phi square and is equal to minus m square, and this is in dividation. When come to this side, come into multiplication, so minus m square fy, and when this minus m square fy kept this side, we're going to get d square fy by d phi square plus m square fy is equal to 0. This is a only phi base variable, and that is kind of simple Schrodinger equation which we have studied in semester 1. So that kind of d square psi by dx square plus d psi is equal to 0. So that way 4 pi square psi is equal to 0. So that way this is a simple Schrodinger equation, but it is based on only one variable, that is phi base variable. Now separation of r and theta. Dividing equation 6 by sin square theta, we're going to get 1 upon r d by dr r square drr by dr plus 1 upon t sin theta. So here sin theta is cancelled out, so this will going to become only r base variable, and here sin theta is there, plus 8 pi square mu r square upon s square e minus v is equal to m square upon sin square theta. So therefore 1 upon r d by r d by dr r square d r by dr plus 8 pi square mu upon s square. That means we kept this theta base equation this side. We're going to get this equation. Equation 8 has only one variable at each side, so the value of the variables are equal to constant. And therefore if we'll take m square sin square theta minus 1 upon t sin theta d by d phi sin theta dt theta by d theta, that value can be taken as beta to abbreviate this equation. If this entire value can be taken as beta and multiplying this equation by t theta, rearranging it, we will going to get n square t theta by sin square theta. This portion, when we multiply by t theta, we're going to get 1 upon sin theta d by d phi sin theta t theta by d phi minus bt theta beta t theta is equal to 0. That is only theta base equation, where this is by mistake written as phi, but it should be d theta. And when you substitute the value over here of beta, we're going to get this beta. Then you can see this is only r base equation, only variable r base equation. So this is only theta base equation, this is only r base equation, and earlier we have separated out phi base equation. Now solution of f phi equation. Equation 5 gives information regarding the magnetic quantum number m, where the value of m would be minus L to 0 to plus L. So d square f phi by d phi square plus m square f phi is equal to 0. That equation having only one variable, that is phi base variable, and that gives information of magnetic quantum number m. This equation is similar with the wave equation of particle in box. So f m phi is equal to a sine m phi plus b cos m phi, and this wave function should be accepted and single valued. So this is the accepted solution of this wave function, and this is single valued, continuous and finite value. That means this is an accepted value for this wave function. According to this equation, fm phi has two equal values, that is either phi is equal to 0 or phi is equal to 2 pi. So when you substitute the value of this phi is equal to 0 one time, you will take fm0 is equal to a sine 0 plus b cos 0, and that value is equal to b. That means b is equal to fm. That is equation 1. That gives arbitrary constant b's value. Now if we take phi is equal to 2 pi, then fm 2 pi is equal to a sine 2 pi plus cos 2 pi. Now b value can be put over here as fm as well. So you will comparing equation 1 and 2, you will get a sine 2 pi plus cos 2 pi is equal to b. This relation turns right if m is equal to either 0, positive or negative value, that is the magnetic quantum moment value, that is also similarly 0, positive or negative integer. So the solution of f phi for hydrogen atom can be represented as fm phi is equal to c exponential plus or minus im theta, where im phi, where c is the equivalent constant, and integration 0 to 2 pi f phi f square phi or f phi into f phi complex conjugate into d phi is equal to 1. Then it is called a normalized wave function, and therefore we will substitute the value c exponential plus or minus im theta over here. It can be represented as c square 0 to 2 pi exponential im theta minus im theta d phi is equal to 1, and therefore c square which is kept outside because it is a constant, exponential 0 d phi is equal to 1. Therefore c square is equal to 0 to 2 pi d phi is equal to 1, and therefore c square is equal to into bracket 2 pi minus 0 is equal to 1. So c is equal to 1 by under root 2 pi, and therefore fm can be written as, instead of value c, we can keep the value 1 upon 2 pi over here, exponential plus or minus im theta, where value of m is equal to 0 plus or minus 1 plus or minus 2 up to infinite. That represent the value of magnetic quantum number. Now real form of fm phi in absence of imaginary value I can be represented as 0 to 2 pi cos m theta cos m phi d phi is equal to pi. Therefore 0 to 2 pi cos square m phi d phi is equal to 1 by 2 m phi plus 1 by 4 sine 2 phi 0 to 2 pi is equal to 1 by 2 sine 2 into bracket 2 pi. So 0 to 2 pi sine m phi into d phi is equal to pi. That way if wave function is taken as m phi instead of cos m phi, we are going to get 0 to 2 pi sine square m phi d phi is equal to 1 by 2 phi plus 1 by 4 sine 2 phi 0 to 2 pi. So we are going to get the integration value 1 by 2 sine 2 into 2 pi. So pi minus 1 by 4 sine 4 pi, and that is 0. So pi minus 0, that is pi. So this value is pi and this value is pi as well. We are going to obtain. Now solution of T theta equation or theta base equation. So for theta base equation we need to consider only theta variable, and that is represented as 1 upon sine theta into d by d theta sine theta dt theta by d theta minus m square t theta by sine square theta plus b t theta is equal to 0, beta t theta is equal to 0. This is only theta base equation where the value of r and phi is abbreviated in the form of m and beta. This equation gives information of angular momentum of electron. Suppose z square is equal to cos theta, which varies between +1 to -1. Substituting t theta by p, we're going to get z square is equal to cos square theta, and that is represented as 1 minus sine square theta, that is equation 2. dt theta by d theta is equal to dp by d theta dp by dz into dz by d theta. So that is dp by d theta, and that is equation 3. So dt theta by d theta is equal to dp by dz. That can be represented as well, and putting that dz by d theta cos theta, we're going to get the equation for dt theta by d theta. So d theta t theta by d theta is equal to minus dp by dz into sine theta, that is equation 4, and d theta by d theta is equal to dp by dz into dz by d theta. Therefore d square t theta by d theta square is equal to d by d theta delta t theta by d theta, and that value if we will substitute over here, we're going to get d square by t theta by d theta is equal to dp by dz d square z by d theta square plus dz by d theta square or entire square, that is dt theta by d theta, that is equation 5. On substituting that value, we're going to get now 1 upon sine theta d by d theta sine theta dt theta by d theta. We need to put that value over here. We're going to get 1 upon sine theta into sine theta d square t theta by d theta square plus d t theta by d theta into d sine theta upon d theta. 1 upon sine theta kept outside, sine theta into d square t theta by d theta square, and this value of differentiation will going to give us cos theta d t theta by d theta. This d square t theta by d theta square plus cos theta upon sine theta is into d t theta by d theta, that is equation 6. Now substituting the value from equation 3 and 5 into equation 6, for this d theta will going to get dt theta will going to get this value, that is equation number 7, where z is equal to cos theta. So dz by d theta is equal to d by d theta into cos theta, because value of z is taken as cos theta, and that value when you are going to differentiate, you are going to get minus sine theta. So d square z by d theta square is equal to d by d theta dz by d theta, and dz by d theta you know sine minus sine theta. So when you put minus sine theta and its differentiation will going to give you minus cos theta, that minus cos theta, so you can put minus z value over here. Thus d square z by dz square is equal to minus z. Now substituting the value of equation 9 into equation 7, you will going to get 1 by sine theta into d by d theta sine theta dt theta by d theta is equal to dp by dz minus z dz square by d theta square into d square p by dz square plus cos theta by sine theta into dp by dz into dz by d theta, that is equation number 10. So that is the solution. Dz by d theta is equal to minus sine theta according to equation 8, when we are going to consider dz by d theta whole square is equal to minus sine theta whole square, and that is represented as plus sine square theta. So 1 minus cos square theta is equal to 1 minus z square, that is equation 11, and cos theta by sine theta into dp by dz into dz by d theta is equal to minus z dp by dz, that is equation 12. Now substituting the value of equation 11 and 12 into equation 10, we're going to get 1 upon sine theta d by d theta sine theta d theta by d theta. That value is equal to dp by dz minus z plus 1 minus z square entire square d square p by dz square minus z dp by dz. Getting the value of, we're going to shorten it out at y minus 1 z square d square p by dz square minus 2 z dp by dz. So getting that value into this equation, we're going to get equation 13, 1 by sine theta d by d theta sine theta dt theta by d theta is equal to this value, can be abbreviated over here, equation 13, and that gives information according to equation 1. We'll have this value. Substituting the equation 13 into this equation, we're going to get this theta base equation. Now taking sine square theta is equal to 1 minus cos square theta, that trigonometry relation, if we are going to use it over here, we're going to get equation 14, and that have value t theta is equal to plus 2l plus 1 l minus m. So we have substituted the value of azimuthal quantum number over here. Beta is equal to L bracket L plus 1 and t theta is equal to n into theta PL mz. The azimuthal quantum number no indicates angular momentum of electron due to its orbital rotation. Well, thank you for paying attention to this video lecture. Keep asking question. As you know, asking question is a beautiful way to gain knowledge. I know that the entire video lecture includes so many calculations, so you may have a little trouble on learning this calculation. So I'm going to put the PDF for this as well along with this, so that you can compare and understand the things together. Thank you.